along with the other authors, Abhijeet, Sashi, and Gayatri. We are part of the emerging AI team with Fidelity Investments. So our team mostly works on upcoming trends in AI, and we try to leverage them to build up solutions for the enterprise. So in this study over here, I'll walk you through our work on leveraging Retrieval Augmented Generative LLMs for automated metadata description generation to enhance data catalogs. So walking through the agenda, so I'll start off with an overview of the problem and an overview about data catalogs, then moving on to the literature survey where I'll cover other studies in the similar domain, and moving on to the solution that we have crafted and individual components within the solution that we want to highlight. Then moving on to LLMs and prompting that we use for generation. Then we'll cover the experiments that we carried out and the results that we observed. And finally, concluding the work with the future work that could also further improve what we have achieved so far. So diving in to the problem overview. So as the British mathematician Clive Humby rightly said, data is the new oil. So data has become one of the most valuable resource in the modern times. And as you can see from the data over here from Edge Delta, like annually we are generating more than 120 zettabytes of data. So that's huge amount of data. And we can understand that there is a need for a good data management setup that would help us tackle all this huge amount of data that we are creating. So in that space, data catalogs come as one of the solutions. So data catalogs help us with improved productivity by reducing people's time in searching for the data and giving them more time to analyze it. So they help with the discovery and collaboration. And they also help centralize critical AI and data governance policies that various organizations use. So in the current market space for data catalogs, there are various players like Alation, Collabra, Altan, and Datadeo. So before we dive further, I want to cover what data catalogs are. So data catalogs, they contain data about the data. So they help people understand the data's content, the physical structure and purpose. So just to give a analogy, so suppose you are out in the market looking for curtains, say, and if you go to a store, so what they will do is they'll probably give you a curtains catalog. It would be sort of a booklet that would have description about various curtains that they have. Like it could have the brand of the curtain, say what texture it has, what material it has, what's the price. So all that would be given to you in a single place or the booklet. So data catalogs also serve a similar purpose in the data architectural world. And some standard form of metadata categories that they are present is technical, operational, governance, and descriptive. Just to dive a bit deeper. So technical metadata, it includes data which tells us, say, about the data types, like is it a varchar or is it a number or a string, or maybe how many unique values are there in a particular data asset or data table. Then there could be operational metadata, which would have like how frequently a particular column in a table is updated, like the information like that. Then there is governance metadata. This consists of data about a certain classification that a particular organization might be using, or is there any certification associated to a particular data asset, information like that. So the last type of the metadata is descriptive metadata. So this would be the descriptions of the data asset. So this could be like, what does a particular table contain, like some description about that. So of all these four types, the first three types are mostly categorical. And while we are curating this metadata, the first three categories these are relatively simpler to curate, and mostly these can be handled easily. But the descriptive part, like where a person really needs to spend some time to understand the data, to create a description, like what exactly does this data asset contain. So this particular task is a bit complex one, and this is where the scaling or like if we want to scale from say one table to say 1,000 table, the amount of effort is also scaled similarly. So this is where our solution would come into picture, and I'll cover that in the coming slides. So before that, I'll try to cover like what a typical industrial scenario would look like. So here you can see how the data hierarchy within an organization generally it would look like. So we would have a database which would be sort of a group of multiple schemas. And within that, each schema would in itself be a group of tables. So, and we all know how like a table is again then a group of multiple columns. So just to quote an example over here, say we have this operations database in which we have a customer DB schema. So within that, we have a table called cust underscore resp underscore t. So this probably means like customer response table or something like that, which is not very evident, but still understandable. But then we have, say, a column name within the table, inv underscore app underscore addr underscore resp in. So for a person who is not directly involved with, say, this table, and if he comes and visits, or if he's trying to find something of value to him, he would not understand like what exactly does this column mean. So it would be helpful for him, like if there is some description associated to the column that would help him understand, okay, what are the contents of this column. And this is where like we would come into picture. So what we have seen like currently in our enterprise, and also while we were doing this research, the same thing resonated with other findings on the internet for larger enterprises as well, that a very small percentage of these tables and columns, they have these description data available for most of the data assets. And also like in the recent decade or so, a lot of enterprises are trying to migrate from their legacy databases to the newer ones and incorporating data catalogs. So again, the scaling of these missing data or missing descriptions for the data, this becomes a huge challenge that people want to tackle. So this is where our solution comes in. So before getting into the solutioning, I'll cover some of the literature that we went through and which helped us curate our solution. So first, like Wilkinson in their study of the FAIR guiding principles for scientific data management and stewardship. So they introduce a concept of FAIR principle, which is findability, accessibility, interoperability, and reusability. And again, in the second study for intelligent cataloging and metadata management, they talk about need for discoverable, understandable, and near real-time consumable data to get relevant insights. So both these studies, they align with the principles of data catalog of discovery and collaboration. So before the very recent times, the initial step in enriching the descriptions or enriching the discoverability was column type annotation. So this CTA, it basically involves annotating columns with semantic type values in each column. So the authors in the other studies, they have tried various methods using knowledge graphs and other transformer-based fine-tuning and even chat GPT to create these descriptions for CTA. One of the drawbacks, although, of CTA is that it relies on the underlying values of a particular table or a particular column. So in a larger enterprise, if you can imagine, like the data from one team, it's not necessarily accessible to the other team. So there are access restrictions that are imposed. So this approach relies on the underlying values, which are not always, like in our case, it is like very few of the cases we would have the full access to the underlying values. So this is a particular limitation which CTA has. So moving on to the other literature. So there are also in the recent 3 or 4 years, a lot of studies have tried to use LLMs for data exploration and discovery. So this study by Alita Lobo for mapping column metadata to business glossaries using LLMs to generate content based on defined context. It's a very initial work in leveraging LLMs. There's also a study by Syed Hosseini for customizing and optimizing LLMs for semantic labeling and modeling tasks. So we try to extend on these works by using the business glossaries along with existing labeled metadata description. We maintain the context relevance by carefully selecting few short examples and employing rule-based filters and preferences. So while we were crafting our solution in our enterprise, there were also a lot of market players that were looking to integrate generative AI into their arsenal for description generation. So this particular task is a well-known one in the industry. Like it is established, like a lot of the databases and data warehouses, they lack these descriptions, and hence players like Collabra and Datadeo, they are trying to implement their versions of description generation. So Collabra uses Google's Vertex AI along with feeding it metadata information like asset name, location, organizational structure to get the description. And even this AI auto documentation by Datadeo is another such solution leveraging open AI models along with the metadata that is present. There are other solutions also present, like Snowflake has its own solution, even Alation has its own solution. But there is a uh, like currently in the current state, these initial solutions, these are mostly out of the box solutions. So they are only suitable for very less complex tasks or very easy defined schemas and tables. And they lack the traceability and reliability due to a black box approach. And since we are dealing with LLMs, there are also a lot of hallucinations possible, and this like creates a barrier for a new enterprise to directly onboard into the platforms like Collabra for their generation capability. So our work would also help like further development of such capabilities within the commercial players. So this is the approach that we follow. Is it probably could be extended to the other market players as well. So going into the data set bit, so this is where we had a lot of trouble trying to find a good publicly available data set in which we could benchmark our findings. So currently in this space, there is very limited data or data sets that are available. VC Slam was one such database, uh, where data corpus, which had around 101 data sets, but there was very limited research that people had done using this data set. So we, instead of using this one, we have been using a proprietary data set from our organization. So another reason being, like when we were working on the company's data set, we could also link with other data stewards and other data teams to verify if the work that we are doing or the generations that we are creating are these of any value, and we could take their feedback and incorporate them into our solution. So the our data set had comprised of over 500,000 columns and over 15,000 tables, a subset of which was further used for fine tuning and creating a repository for our examples, which I'll talk about. So for evaluation purpose of the study, we have used two data sets. One is an existing route to data set, and one is a data stewards feedback data set. So I'll come back to these two data sets in the evaluation section. So moving to the solution overview. So we have a bottom-up approach over here. So what we do is we start with trying to find out the descriptions for the columns. And since a table is like a combination of columns, so once we have descriptions for columns, we can then use, like intuitively, it would make sense. Like if we know what individual columns mean, then we can aggregate that knowledge to define or to create a description for the table. So this is a bottom-up approach that we try to follow over here. And the two pipelines over here, the upper one is for column description generation. So I'll talk about the individual components in the coming slide. So basically we have the column inputs. So these inputs could be the example that I quoted, like the database where they're coming from, the schema which they belong, the table, and the column name, obviously. And apart from this, there could be some other data also available. Like we could have some business glossary, like business terms defining certain columns. There could also be some user comments, like user comments generally are very short descriptions, like maybe 5-6 words. People could just quickly type in, like while curating the initial table itself. So all those information could also be present, like which we also use. I'll come to that. So the first step being pre-processing the text. So this would involve removing, say, HTML tags or any symbols or other things, like basic text cleaning. Then there is a component called expander pipeline. So this is a component in which like if you have this column name, so it is difficult to understand like what INV or APP would mean. Like, so this expander pipeline, basically we try to expand like what INV could mean, and we try to feed that knowledge to the LLM. Then the third component being the similar example retrieval. So this is another like the RAG part of the pipeline. So here what we try to do is, for a particular column, we try to find from the existing database, like whatever, say 5 or 10% of good curated data that we have. We try to find like if there are any good examples that are similar to the one that we are looking for. We try to find those similar examples, and all these three things, we try to combine it into a prompt and feed it to the large language model to get a description. So these descriptions are then further reviewed by a steward, and they are like if they're accepted, they flow back to our repository for the good examples that we can again leverage further. So once we have the column level descriptions generated, so the table level is also some form similar, just that here instead of similar examples retrieval, we use the generated descriptions for column, and we try to sample a few columns from them, and like combine them into a prompt and feed it to the language model to get the generation. So this is again an elaborated example of the pipeline that I was showing for column generation. So like we have this expander pipeline in which like INV, it could map to individual or investment, like INV stands for what. So there is some form of disambiguation which I'll come to in the details of the expander pipeline. So again, like we have these retrieved examples. So in retrieved examples, again, like INV APP underscore IN. So what we try to do is like whatever individual segments that are present in the full column name, we try to find like if there is an exact match, then that is good. But if there is not an exact match, we try to like find most number of keywords that we can cover through the examples that we try to find, and we use those in the prompt, like which would have sort of a system message in which we instruct like you are a data steward and we are looking for some descriptions. We pass them these two examples, and along with the other expanded form of the column name and other information for the model to generate. So details of the expander pipeline. So again, like we start off with again some word like this, probably separated by underscores or spaces. So we split the words. The first check is like we look if it is a word or not. We were using PyEnchant along with NLTK vocabulary with some further modifications to check if it is a known word or not. If it is already a word, we don't expand it. If it is not a word, then we have this abbreviation mapping. So this is custom curated mapping. Like this was also created from the database that we already had, along with like further modifications as we improve the process. So if a particular mapping is found, then we try to disambiguate it. Like in the previous example, like there could be multiple expansions also possible for a particular abbreviation. So we try to look like if in a particular table, if the mapping is like if for a particular table, if that expansion is unique, or if a particular schema, if that is unique. So in this stepwise form, we try to disambiguate it. And if even after all this, we are not able to say like, okay, this is a unique definition for this particular abbreviation, then we do not expand it and we leave it for the LLM to expand. So the reason why we are doing it is like in our experiments, we found out like if we do not give the LLM the expansions for these abbreviations, since LLMs, they have like all their worldly knowledge, they try to expand it on their own, and they in the process they hallucinate a lot. So they could create wrong expansions and hence create the entirely wrong context of what the actual column would mean. So similar examples retrieval. So this is the RAG pipeline. So in which we have a column name. So we would have a vector store which would comprise of the business grocery. So which would be the standard business terms, and also the good examples which we sequentially create, and even whatever existing, say less than 10% that were there. So we try to find top 100 examples of the column that we are looking for. So within this, if we have an exact match for the name, then again, there is some sort of hierarchy, like we look in the same table or same schema, then same database, and we try to pick that particular right example. But if there is not a right examples, then again, we try to do something like this, which is a LCS re-ranker, so longest common subsequence. So individual keywords, we try to find 2 or 3 examples that could combine to form, say, the entire column. It could spell out the entire column. Moving on to the LLMs and description generation. So as the first step, we try to fine tune our model. So we were a bit restricted on the resources that we could use. So we employ QLoRa technique, which is a quantized low rank adaptation. And we fine tune a Llama 2 7B chat model. At that time, Llama 2 was the new model. So we haven't explored the newer ones, which again is part of the future work that we could explore. So we use a validation split of 90-10 with a rank of 64. And the fine-tuning dataset, it had over 35,000 pairs of prompt and responses. So prompt is the one similar to what I had shown, and responses were the label dataset or the good quality dataset that we already have from that less than 10% label data. So this training was done for one epoch. Actually, for if we went further than one epoch, we could find some overfitting over here, in which the training loss was lower than the validation loss. So we like trained it just for one epoch. Apart from fine tuning, the second approach was to use fewshot prompting. So this is like the default approach we now have. So this we use GPT 3.5 Turbo for columns and GPT-4 for tables. The reason being, GPT 3.5 at the time was around 30 times cheaper, and the amount of columns that we have, it's much larger than the amount of tables we have. So to balance the cost out, we used GPT 3.5 Turbo for columns. And because GPT-4 has this advanced reasoning capability, so for tables it made sense because we had a lot of columns. It had to assimilate the knowledge into one description. So GPT-4 made sense for that. So this is a sample prompt, as I also mentioned earlier. So we have a system prompt, some of the examples retrieved, and the information that we have for the current column. We try to combine them in the prompt and feed it to the language model. Now coming to the experiments and results. So the evaluation set that we have, it has 2 data sets. One is the existing ground truth data set. So this data set is the validation set created by sampling, like what I mentioned, from that 10% good data, say, that we had. We sampled a few examples, good quality examples, across different schemas and databases, and we created this data set of over 8,000 columns and 122 tables. Then there is this second data set. So this is where we approach data stewards. Data stewards are the people who are responsible for creating these descriptions in the first place. So what we do is we try to generate these descriptions. We share these descriptions with the data stewards, and we ask them, like, if there are any modifications they want to make to the description, they can make the modifications. And then we study, okay, we had given them this description, okay, they have removed these words or they have added these words. And then we try to study, okay, how much change is actually required from what generations that we are sharing with them. So these are the 2 data sets that we used. So the results. So first, talking about the existing ground truth data set. So this is the good quality descriptions that we already had. So for the remodels, we are comparing them across BERT score. So BERT score is basically to compare the semantic similarity between the reference and the generated one. So the ground truth and the generated description in this case. So we can see, like, Llama 2 13 billion. So this is the pre-trained model. It's not the fine-tuned model. It performs a bit worse than the GPT 3.5 Turbo and fine-tuned Llama 2 7 billion over here for the column description task. So this is for the ground truth data set in which we try to find the BERT scores. For data stewards feedback, like the data in which the steward would correct any mistakes that the generated description could have. So for that, we try to use Rouge-1 score. So Rouge-1 basically, it does not look into the semantic level, but it mostly relies on like what changes or what individual words are present or not. So based on that. So in this, we can see like the Rouge score for the table descriptions column, like for column descriptions is it's close to 0.87, and BERT score of 0.9 means like almost 85% of time the descriptions are good to go, like as is sort of thing. So if you see acceptable with or like minor edits, there were 88% of descriptions out of that were accepted like as is or with very small edits. So now coming back to this, like if you see like GPT 3.5 Turbo, the scores are a bit less compared to the fine-tuned Llama model, but the final model that we have used is GPT 3.5 Turbo. So there is an interesting reason behind that. So when we were going through the generated descriptions, from a personal perspective, we were finding out like GPT descriptions look good, like, but when we were looking at the scores for BERT score, the fine-tuned Llama scores were looking better. So we tried to dig deeper, like what exactly is happening. So what we found out is like during the fine-tuning process, the fine-tuned Llama model, it had learned a lot of that language, the way the descriptions were created, and a lot of exactly copying thing it was trying to replicate. So this is a table in which we show like out of all these instances, around 50% of the times the fine-tuned model was trying to copy whatever we were trying to pass it in the context, or trying to copy from a similar example that it had retrieved. So and what GPT was doing, it was trying to paraphrase it. So the BERT score was a bit lower for GPT, but overall it was better. So how we tried to like evaluate it further was using align score. So this align score is another metric. It's basically a Roberta model trained for context and claim. So what it tries to do is, given a context. So for us, the context would be whatever information we are providing in the prompt. That could be the example, the data we have, the information we have. So all that information, and the claim would be the description that is generated. So what we try to do, what align score does is it tries to see like if the particular claim, it can be explained based on the context that we are providing. So it has this alignment scores. So if a particular information that we are giving as a response, is it really given in the context, it tries to figure that out, and it assigns a score, a high score meaning that it is aligned, and a lower score meaning it's not aligned, or probably the model is hallucinating or creating information. So these are the experimental results. I'll try to walk you what the axes are. So the x-axis, it contains the ground truth alignment. So what that means is, suppose we have whatever context we are providing to the model. So that context is same like across the models. That would be the retrieved examples and the information we have for the column. And then we have a ground truth. So we tried the ground truth alignment score is basically if the ground truth can really be explained from whatever information we have in the prompt. So a high alignment would mean that, okay, the ground truth description that we want to generate, yeah, this is possible to be generated from the prompt. That would mean a high ground truth alignment. And a low ground truth alignment is probably like we don't have enough information for the model to be able to create that ground truth description. So that is the x-axis. And then we have these align score in the first block, and the BERT score in the second block. And these four figures, these are of scenarios like in which we have an exact example. These two are for exact example, like what examples that we are retrieving. We have a like exactly matching name for that, we have it or not. And these ones are where we do not have exact examples. And the top ones are for the ones in which like there are additional comments, which I mentioned, like user comments or business glossary. So if they are missing or if they are present. So and the three models that we study over here are, blue one is the Llama model, the pre-trained model. The orange one is the GPT model, and the green one is the fine-tuned model. So some of the observations that we have from this is, for both fine-tuned and GPT model, the uh, prompt inputs, they entail with high align score wherever there is a exact match columns are retrieved. So in these two, you can see like the align scores are pretty high, like more than 0.6. So which is a good thing, and it would also make sense if we have good information in the exact example. But however, wherever there are like partially matched examples, we see that GPT model performs better than the fine-tuned model. So in the examples over here where there is no exact match, you can see the orange dot where the ground truth alignment is higher is above the green dot, which is the fine-tuned model. So the alignment of the GPT results are better to the information that is being provided to the model. So this is how we concluded that, yeah, the GPT model could be a better suit for our use case. And then again, the pre-trained model, although it does well, but compared to the fine-tune and the GPT model, it has lower BERT scores and the align score as well. So coming to the conclusion, so in this paper, we propose a smart data catalog, LLM-based framework with fewshot retrieval and additional existing attributes to generate description. So the research, in this research, we tried to do extensive experiments with prompt enrichment, like bringing in domain knowledge to propose unique components like the fewshot retrieval, the examples that we retrieve, and the expander pipeline. So we try to incorporate all these so that we can give good context and assist the LLM in generating more accurate descriptions. So this is the overall work, and as future work, there are some avenues that could be explored. Like in the last year or so, there have been a lot of newer LLMs and fine-tuning techniques which could be explored. And with larger context windows, it also gives us the ability to incorporate more knowledge. Like there could be knowledge articles about various schemas that are present with the enterprise that could be leveraged. Then there could be data augmentation for the prompt that could be done. So basically, further values, like if there is access to values of say a column or a table, so those can also be augmented in the prompt, and the model can generate a better generation. Then data model or data lineage, like how the data is structured within an organization. If we have a way to incorporate that into a prompt and context, so that could also further aid the generation process and give more accurate descriptions. So yeah, that is it. Thank you for your time, and that's it from my side.